In this module, we will explore the basics of electromagnetics, the why is it important, why do we need to study electromagnetics, and the basis of electromagnetics. We will also touch on the important applications of electromagnetics and how it affects our everyday lives. Electromagnetics is very important to the advancement of electrical engineering. Our technologies of today depends a lot on electromagnetics. In fact, without electromagnetics, you wouldn't be hearing me in this recording. So our communications depends on electromagnetics. It would not be possible to communicate between two distant locations without electromagnetics technology. To the average person, electromagnetics can be difficult because it utilizes two, uh, two of the basic fields that occurs in the universe, the electric and magnetic fields. They are three-dimensional and are vectors, and they are governed by uh, partial differential equations. Um, it would be difficult to analyze and solve problems pertaining to electromagnetics without the use of advanced math. So mathematics here will be a crucial tool in our study of electromagnetics as we go along. The very basis for electromagnetics is the property of subatomic particles called charge. And the study of charges that is at rest or in motion is called the electromagnetics. Electromagnetics can be divided into three branches. We have electrostatics, which is about charges that are at rest, magnetostatics, charges that are in motion, in steady motion, so there is no variation uh, in time of these charges, and electrodynamics, which is really the subject of charges that are not only in motion, but their motion changes over time. That gives rise to a propagation of energy and information. In atomic theory, we know that an atom consists of subatomic particles. So we have the electron, the proton, and the neutron. Electrons possess uh, a negative charge, while a proton possess a positive charge. A neutron, while having a mass, has no net charge. Now, an object in its natural state can be a neutral object. That simply means that the amount of positive charge in the object is equal to the amount of negative charge in that object. So therefore, that object has no net charge. Uh, but once the object has, let's say, an excess of electrons or an excess of negative charge compared to the positive charge, that object will possess a net negative charge. And the other way around would be also that if it has an excess of positive charge compared to its negative charge, that object is considered positively charged. So electric charges can be of two types. We have the positive and negative charge. So a proton is a positive has a positive charge, an electron possesses a negative charge. Now, the measure of how much charge there is on an object or on a subatomic particle is measured by the a unit called coulombs, and an electron or a proton has a charge of this much, 1.6 times 10 to the negative 19 coulombs. So it's a very small number, and in fact, to uh, create 1 coulomb of charge will require this much electron. So it's a very large number. Electric charges has this property that if you put them together near each other, a force exists between them. In fact, if I let two unlike charges or like charges near each other, a repulsive force tends to keep them away from each other. On the other hand, if I put unlike charges near each other, the tendency is that an attractive force exists between them. Positive and negative charges are producers of electric field. For example, if we have two unlike charges, a field will be produced that looks like this. So a field that is directed from the negative charge going to the negative charge exists. This field even becomes prominent as the two charges becomes near each other and becomes less prominent or less stronger if they are farther away. Transfer of charges between objects is possible. So let's say we have two objects, and let's say one object has uh, equal amount of negative and positive charges, same as the other object, and well, the body that loses electrons has an excess of positive charge. Now, uh, usually the charges that moves from one body to another are the negative charges because in normal situations, electrons are the ones that transfers from one object to another or from one atom to another. So let's say um, these electron transfer to that object. This object will now have an excess of electrons, but the other object has now a deficiency of so this electron will now be gone, or this negative charge will now be gone, and therefore this object will now have an excess of negative charge, and therefore it becomes negatively charged. While the other hand, the one that loses a negative charge becomes positively charged. But uh, the entire system, so let's say we consider this as one system, is still neutral because the amount of positive charge and negative charge is still the same. The basis of electromagnetic fields are charges that are either at rest or in motion. Positive and negative charges are sources of electric fields, and when the electric charges move, they will yield a current that creates the magnetic field. Time-varying electric and magnetic fields are coupled with each other to create a magnetic field, that radiates from a source. A time-varying electric field intensity E that creates the electric flux D will give rise to magnetic flux density B and magnetic field intensity H, and vice versa. So what do we mean by this is that, for example, we have an antenna. Now this antenna creates a current flows to that antenna that creates the electric field. So this gives rise to an electric field. Now this electric field will create in the environment a current, a varying current that creates the magnetic uh, field, okay, magnetic field intensity, and that magnetic field intensity will again create current that will again create the magnetic field. So it's a cause and effect situation where one field creates another, and in the process creates what we call an electromagnetic field. Now, because of this cause and effect, the result is that we will have a moving electromagnetic field. Two fields that are perpendicular with each other and moving in the direction uh, that is normal to both the two fields. So this is how it looks. So it starts from here, from the source. Let's say this is an antenna. So an electric field is created because of the varying current through the antenna. It creates an electric field. So this electric field, now while this is created, a magnetic field is also created as the effect of the variation in electric field. And both of these fields move in this direction, which is normal to both of the fields. So these are the quantities involved in an electromagnetic field. So what we have here is the electric field intensity, and as a result, we'll create the electric flux density that will actually create the current around it that results in the creation of the magnetic field intensity, a varying quantity as well, that results in a magnetic flux density. So it's like that the cause and effect is in this direction, and then it moves back to create the electric field intensity, and the cycle goes on. So that gives rise to a moving electromagnetic field. So these are the quantities involved, and these are the corresponding SI units. Electromagnetics has many applications, and one of those are these technologies used in communications. So we have our cell phone nowadays that can communicate with other mobile phones, and also our television sets uses electromagnetics. Some of their functions there uses electromagnetics. We also have computers. So we have wireless routers, usually found in our homes. laptops, and antenna as well, speakers, and also very prevalent in military. We use it in radars and also in medical applications. So these are also several of the applications of electromagnetics. So to name a few, we have microwaves, for example. We in microwave communications or even in the microwave appliances that we have at home, it uses electromagnetic technology. So in our microwave appliances, we use their electromagnetic power to heat the tissues and stimulate certain physical responses. In the electromagnetic fields, we also use them in one of those kitchen devices. We have induction heaters, for example, that nowadays use electromagnetics for cooking, and many more applications of electromagnetics. In the study of electromagnetics, there are several constants that we will encounter, and these constants are called universal constants. So one of these very common constants is the speed of or the velocity of light in free space. So this is the velocity of light in free space or perfect vacuum. We also have permittivity in free space. So the permittivity affects how electric fields are formed. So they affect the ability to transmit electric fields. So in free space, the permittivity is given by this constant. We also have permeability, and this one affects the magnetization of materials and describes the ease to which magnetic flux is formed. For free space, this is the permeability. Okay, these constants are related by these set of equations. And we also have what is called the intrinsic impedance of free space, and it is given by this one. Electromagnetics are governed by the fundamental laws. So under electrostatics, we have the laws in electrostatics, those that pertains to the creation of electric fields. We also have the laws under magnetostatics. So these are laws that pertains to uh, the creation of magnetic fields. Now the combination of both we will yield the laws pertaining to the combination or the electromagnetic fields. And in fact, the laws in circuit theory comes from this field. Now, all of these are defined under the umbrella equations by Maxwell, uh, which we will encounter as we go along with this topic. The spontaneous creation of electric and magnetic fields starting from a source gives gives rise to what we call the electromagnetic waves. So these waves moves from the source and has a frequency. Its frequency depends on the frequency of the source. The frequency of the source depends on the type of applications that it uses. So for example, if the frequency range is this one, so this is the frequency range used in AM, radio, maritime, and direction finding. So as these frequencies decrease, their applications the applications actually differ. So different applications uses different sets of frequencies. So as the frequency increases or decreases, we notice here that the wavelength of the wave increases. Here we have more frequency ranges and applications. So for example, the range of frequency used in our TV uses these range of frequencies, or what we call the very high frequencies. So more frequency classifications. This table here shows a summary of the different classifications per applications. So it's here, and the frequency range that these applications uses and the corresponding wavelength. Now, on our next video, we're going to start on vector analysis, and these is the building blocks that we need to understand uh, to deal with the analysis of electromagnetics.